So in this today's lecture, we will discuss some important phenomena related with nuclear physics, that is the discovery of radioactivity, and then we will talk about the surprising various applications of this radioactivity, and then we will discuss what are the various implications of radioactivity, and what are the various different particles which come out of the nucleus, like alpha decay, beta decay, and gamma decay, and some other four sort of particles which are the result of this artificial or natural radioactivity. And then we will discuss about the attenuation constant and how these uh, particles, they are decayed with respect to time with this radioactive decay law. And then we will talk about what is the half life of a period, what is the activity or decay rate of a particular substance, and how we can find out the average life of a particular atomic nuclei. And then we will discuss about some discussion about the alpha particle. We will discuss Geiger-Newton law, and then we will discuss about the famous tunneling, quantum mechanical tunneling of alpha particles, and then we will do some sort of numericals related to these topics. So this development of this scientific thoughts in the 20th century, so the all it happens, the origin, it is due to the discovery of radioactivity. You all know that in 1903 the Curies, the husband and wife, they were awarded jointly with Becquerel the Nobel Prize in Physics for their discovery in radioactivity phenomena. And after the discovery of this radioactivity, so there is the discussion of quantum concept which comes into line, and then the Einstein explained about the famous quantization of light, that is the photoelectric effect of its light, and based on that he explained about the mass energy relation, that is the famous energy of special theory relativity, and how the mass and energy it is being exchanged. And after that, the Rutherford, it explained about these natural radioactivity, how the transmutation of these particles which is happening, and due to that there is alpha, beta, and gamma particles which are coming out of the nuclei. And further the development of this atomic nucleus, and the process goes on. So this the most important years of this radioactivity discovery, they are lying in between these 1800, 1906, and 1913. So these are quite important discover years in which the many discoveries related with radioactivity, so they are have been published by various scientists. And so what is basically the radioactivity? So the radioactivity, it is the spontaneous decomposition of a nucleus. So it is forming a different nucleus and producing one or more additional particle. And Becquerel was he was doing his past PhD thesis, and he found out this famous theory of radioactivity from this pitch blende substance, that is the oxide of uranium, uranium oxide. He found that, so this substance, it is undergoing some sort of photoluminescence, and it is eliminating some particles which are brightening in the dark. And he found that these some sort of particles which are coming up from this uranium dioxide or pitch blende. And from that he said that during this radioactivity decomposition, so one particle, it is being converted into another particle by eliminating any other particle. So this particle, it can be a beta particle, it can be a gamma radiation, it can be a positron particle, it can be alpha particle. So depending upon how these parent nuclei, they are being converted into daughter nucleus. So the basic idea happen. So why this is being happening? So this is because of some sort of the nucleons interaction which is being continuously changing. And as you all know that the strong nuclear forces, there are two type of forces which exist within the nucleus. So one is the strong nuclear force, and the second is the weak nuclear force. So the strong nuclear force, that is due to the mesons which are binding these nucleons, and the force, it exists up to a range of 1 to 4.2 femtometer. And Further, so there is some sort of force which is known as the weak nuclear force, and these forces happens when these neutrons and protons, they are converted from one to another. So these two types of forces, there is exchange of this force, which is the result of the particles which are coming out of the nuclei. And there are like in everyday life, you will see how the radioactive materials, they are being converted into the daughter nuclei. So the famous example to found out the radioactivity material is the smoke detector. So these you have been seen in all of their houses, like it is quite famous in Western countries. So smoke from a fire, it can be detected at a very early stage. So similarly, so these fire detector or these smoke detector, it can detect any sort of radiation which is present in that particular environment, and those radiation or those smoke, so when they interact with the filament of this smoke and they generate some sort of electric current, and due to the generation of this electric current, so there is some sort of a circuit which is getting completed, and you can see that there is a siren which is getting honk up, and the people get alert that something is fishy within those environment. And the other example of radioactivity material, that is the fission reactors. So when you are undergoing a nuclear chain reaction, and you will see that when this uranium nuclei, it is being bombarded with these slow energy neutrons, and it is being decayed up into barium and krypton. So there is some sort of noise. So somebody has not muted its mic. So please mute everybody mic. Yeah. So somebody's mic is not muted. Okay. So in this nuclear fission reaction, you can see that, so when these neutrons which are being generated in this fission phenomena, and there are chances that these neutrons, they can be leaked up in the surroundings, and due to that, so these nuclear reactors, they are present around the sea, so where there is a huge amount of water, so that we can liberate or generate those heavy energy neutron within these water. And so we can see that if there is a leakage of these neutron, and we can detect those leakage of neutrons from this radioactive material. So this is also the example of this application of radioactive material. So other application of this radioactive material is the scientist, the agriculturalist, they understand the detailed mechanism how plants, they utilize this phosphorus in growing or reproducing. So they are applying some sort of radioactive material, and then they see the effect of the growth of the plant, so it is being impacted by these particles. So there are some other important application in food technology. You can see that we can enhance the life of some fruits like apple, strawberry, by irradiating these fruits with some sort of radioactive particles. Like these particles, they generate gamma radiation or neutrons, and which can destroy the bacteria which are present on the surface of these fruits, and we can enhance the life of these bacteria. And in these days, there is a quite work which is also going on this agriculture and on this food technology, so using the cold plasma therapy. So we can generate some sort of cold plasma, and on the basis of this dielectric barrier discharge plasma or atmospheric pressure plasma, we can enhance the life of these fruits, or and we can save these fruits up to like for many weeks. So these are some of the applications. So how this idea of this radioactivity, it comes into the line. So this was the scientist Henry Becquerel, whose earlier work, it was concerned with the plane polarization of light. So with the phenomena of phosphophones, with the absorption of light, so he was looking at some sort of a photophosphorescence from some crystals, and he worked on this subject in the 1896 and followed this discussion with this Henry Poincaré on the radiation. so which has discovered these X radiation. So he accomplished a type of photo phosphorescence in the vacuum tube. So then this Becquerel decided to investigate whether there was a connection between these X-rays and the some naturally occurring photo phosphorescence. So he was inherited from his father by supplying some sort of uranium salt, so that is known as this pitch blende. So when the salt they were placed near to a photographic plate covered with opaque paper, the plate was discovered to be opaque or this fogged. So this phenomena was found to be common in all of these uranium salt, and these concluded that the ray emitted from this uranium, which for a long time were named after this discovery, and he gave the name to these radiation as Becquerel radiations. And these radiations they were different from X-rays. So from his discovery of this spontaneous radioactivity, Becquerel was awarded half of the Nobel Prize in Physics in 1903, and half of the Nobel Prize it has been shared by Marie Curie and her husband Pierre Curie for this further discovery of these Becquerel radiations. So half of the discovery it has been done by Marie Curie and Pierre Curie. So these were the Nobel laureates. So Marie Curie, it was the first Nobel laureate who got the two-time Nobel Prize in the physics field in 1903 and in 1911 in the field of chemistry. So she also became the first woman to be appointed to teach at the University of Sorbonne. So she was born in a small town Pole in Warsaw, and he spent his early years in 1891, and she moved to France at the age of 24, and where she started her higher degrees and he started his scientific career. So at this Sorbonne University, she met and married with some another instructor, that is the Pierre Curie, and together they study radioactive material, particularly this pitch blende. So because this pitch blende it has some quite unique properties, and they further discovered this pitch blende, and in 1898 they deduced a logical explanation that the pitch blende it contained traces of some unknown radioactive components, which was far more radioactive than uranium. So thus in December 26th, the Marie Curie announced another radioactive particle which is present in this pitch blende, and they named this particle as polonium. And later they found one another particle, that is the radium, which is present in this pitch blende. So these are the two new particles they found from this pitch blende, and due to these discovery they got the Nobel Prize in Physics and in Chemistry in 1911. So later you will surprised to know that the Marie Curie has been killed due to this heavy, because she spent most of the time in the labs, and she has been cured with cancer due to heavy dose of this radioactive substance. And these substances they are the major reason for her death, and she has been died due to these radioactive substances. So the discovery of these uranium, radium, and some other radioactive substance, they triggered some potential applications in the field of medical and industrial field. So some people they surprised to know the properties of these substances, like the radium. It can have those unique properties which can make a blind girl she can see, and something like these are some of the papers they have been published. And some of the other applications which are quite unique, that the popular product they have been designed based on these radioactive substance, like the radioactive toothpaste. So people start to use for cleaning teeth and for better digestions. So they use some sort of face cream to lighten up their skin. So someone use these as the radioactive hair tonic. And some people, they try to eat the radium laced chocolate bars, and because these chocolates, they rejuvenate and they excite, they enhance their blood pressures, and they feel quite good after eating these chocolates. So these are some of the discoveries which are quite people quite curious, because they are directly related with their biological impacts. And some of the discoveries, so some people, they tried, so it was a little strange, that when somebody, they blew her nose, and her handkerchiefs glows in the dark. So that person who is eating those chocolates, everyone knew that the stuff, it was harmless. And the woman, sometimes they even painted their nails and their teeth to surprise their husbands or boyfriends. So when she opens her mouth, and these radioactive or radium elements, they glow up in the dark. So, according to this Department of Commerce, later they declared that the excess dose of these radioactive substance, it is quite harmful, and it can cause cancer to these humans. And later on, there are some peoples which has been found cancerous on their tongue, on their bones, due to this excessive use of this radium exposures. So after that, in 1952, so the discovery of this artificial radioactivity, so people becomes quite aware about these radioactive substances, and they stopped using the excess dose of these radioactive substances. So after the discovery of this radioactivity in 1903, so the famous scientist Rutherford, he gives the important explanation about this natural radioactivity. So this Rutherford, he said that these radioactivities comes due to these emission of some particles which are coming from these radioactive substances like alpha, beta, or gamma particles. And a radium atom, it emits an alpha particles, and it turns into a emanation, and this atom, it turns emit to another particle, and then it changes its identity from emanation to radium A, and further it emits some other particle, it changes its identity to radium B, and so and so. So these radiation or these photoluminescence, so it's being changing as these particles, they are emitting different radiations. So later, so they have found that there are various isotopes which can be possible. Like you can see that these radon, so it has many isotopes. Some of the isotopes who has a very small half-life, that is of the order of 4 days to 12 days, and some radium isotopes which is having a very large half-life, that is of the order of 1600 or many years it can be. So it depends upon the nature of those substance, or how some substance, they are more stable as compared to other substances. So this has been later discovered, like when the concept of this binding energy, it comes into line in the 1920s. So Rutherford, it has been known as the father of this nuclear physics, and Rutherford got the Nobel Prize in physics by their discovery of natural radioactivity. So he was from New Zealand, and he got the Nobel Prize in chemistry in 1908. That is due to the discovery of natural radioactivity. And you will be surprised to see that his famous work that has been comes after the when he got the Nobel Prize, and after that he found he done many major research on the field of like alpha scattering experiment. Then he explained the idea about the nucleus, and how these nucleus, it is consist of neutrons and protons. So all his work, it has been published once he got the Nobel Prize. So this Rutherford, it was appointed to the chair of this very famous university in Canada, that is the McGill University. So where he did the work, so which gave him the Nobel Prize in chemistry in 1908. So he had demonstrated that the radioactivity was the spontaneous disintegration of atoms and he noticed that a sample of radioactive material, it invariably took the same amount of time for half the sample of the decay, and he gave the term half-life as well. So he explained the phenomena half-life period of substances, and in 1907 he took the chair of physics at University of Manchester in United Kingdom. There he discovered the nuclear nature of atom and was the world's first famous successful alchemist. He converted nitrogen into oxygen. So while working with his student Neil Bohr, who discovered that electrons move in specific orbits, so Rutherford theorized about the existence of neutrons, so which could somehow compensate for the repelling effect of positive charges of proton, so which are present in the center of the nucleus, and he also originated the term nucleus. So we will not talk about this Rutherford alpha scattering experiment because I have already talked in detail in my first lecture. So you can have a look and you can see that how this alpha scattering experiment, it gives us the idea how these nucleons, they are present within this nucleus. So radioactive material, it undergo nuclear decay. So after the discovery of this natural radioactivity, so people found that the atom, it was considered as the elementary particle. So they violated the idea that atom are the unchanging, indivisible, and ultimately building blocks of matter, because after this discovery they found that there are some other particles which are present within these atoms like electrons, protons, and neutrons, and they can be the building blocks of the particles. And later the discovery of quarks in 1960s, so they have found that these are not only the elementary particles, so these can be further breakdowns into quarks. So additional experiments with cathode ray tubes and so mass spectrometers, they also showed that atoms do consist of small components like proton, neutrons, and electrons, and which violate the idea of atoms to be considered as the elementary particles. So some of the terminology which we will use in this radioactivity is element. It is considered as the simplest stable building block of material which consists of proton, neutron, and electron. So radioisotope, it is considered as an unstable isotope that undergo nuclear decay. Radioactivity, that radiochemistry, it is the study of radioisotopes, and the nuclide, it is generally defined for each unique atom which is present in this modern periodic table. So most common particles which are emitted by this radioactive materials are alpha particles, which are also known as helium nucleus, and which we generally define with as 2 helium 4, where this 2, that is known as the atomic number, 4 is known as mass number, and here we generally represent this with the symbol He. And the beta particles, they are also considered as the particles which are coming out due to this radioactive phenomena. There can be beta plus particle which are known as positrons, gamma radiations, neutrons. They can be emitted from this radioactivity phenomena, and we will discuss like the beta decay in our next lecture, then gamma decay in detail in our next lecture as well. And in our today's lecture, we will concentrate more about the alpha decay, in how this happens due to this radioactivity. So in alpha decay, you can see that here this radon, it is emitting some alpha particle, and you can see that it is being converted into this radium is converted into radon by the emission of this alpha particle. Similarly, this thorium, it is being converted into radium by the emission of this alpha particle. So when there is an emission of alpha particle, so the atomic number, it decreases by 2, while the atomic mass, it decreases by 4. So because these 2 and 4, it has been goes to the alpha particle, and along with that there is some sort of energy which is being also liberated. So the net effect in this alpha particle emission is the loss of 4 in mass number and loss of 2 in this atomic number. And in beta particle, you can see that The net effect is change of a neutron to proton, and when there is a change of neutron to proton, and along with that, so you can see that the atomic number it increased by 1. So for example, here thorium it has atomic number of 90, and with the emission of this beta minus decay, so its atomic number increased by 1 while the mass number it remains same. So these are some of the examples of this beta minus decay. So these are some of the examples of beta plus decay. So in beta plus it is opposite to beta minus decay. So in beta plus there is conversion of proton to neutron, and due to this conversion of proton to neutron within the nucleus, you can see that the atomic number it is decreased by 1 while the mass number it remains same. So you don't need to calculate every time, so you can look at the reaction and then you can tell whether the emitting particle it can be a beta minus or beta plus, because sometimes they can ask about the energy of these particles. So in gamma radiation, so gamma radiation can be by any way. So the net effect is in this gamma radiation no change in mass number or no change in atomic number. So this gamma radiation it can be some excited nuclei when it liberates excess of its energy, and then it can decay to the ground state by emitting some sort of gamma radiations. So this is another example of radioactive decay, that is the electron capture. So in this electron capture process, the inner orbital electron from this atomic electron it is being captured, and the new nucleus it is being formed, and this along with this neutrino and gamma radiations they are produced. So you can see that this murky nucleus it has captured this electron, orbital electron, from the nearest closed orbit, and this mercury is being changed into gold. And during this electron capture process and the beta positron process, you can see that so there is the atomic number it is being decreased by 1. So these are some of the examples. So net effect is change a proton into a neutron, so that is the same. So what is basically happening in this radioactivity reaction? So there is a conservation of mass number and charge number, which is always remain same. So both are retained in this nuclear reactions. So sometimes you have been asked to balance a chemical nuclear reactions. So then you have to balance these reactions by conserving this mass number and charge number of reactant and products, and then you can find out what will be the this daughter particle or some other particle which is being emitted when this parent nuclei is being converted. So these are 5 type of reactions which are being happened in this radioactive processes: beta particle, positron emission, electron capture, alpha particle, and gamma radiations. So if you look at this famous mass parabola graph, so there are almost 2,850 isotopes which are plotted versus their charge density, and they form something like a parabola. And you can see that these open symbols they are the radioactive nuclide, while these filled nuclei they are the stable and having the long-lived nuclei. So they have plotted the free neutron. So you can see that this free neutron it is the most unstable nuclei, most unstable, and this proton this is considered also as the unstable. So more this graph it is towards this lower value of M or A, so higher is its stability. So at this point you can see that iron 56, so which is having the lowest value of this M over A, so that is considered as the most stable nuclide of this periodic table, and which is having the largest number of isotopes as well. So the further the particles which are from this parabola, so the more unstable they are. So you can see that the radioactive elements, so they have having higher values of M over A ratio, and you can see that. So that's why this open symbols, they are quite present at this upper level, and they are quite unstable. So these all are the radioactive elements which are quite unstable and having the larger ratio over m over a. So from this Mar parabola graph, you can find out which isotope it is having the more stability. Hello, can you listen me?
Yes, sir.
Okay.
Yes, sir.
Okay. So this is another very important graph. So this is the cradle of the nuclide, and you can see that the proton-rich isobars on the right side of this valley. So here, oops, just a minute. So these are the proton-rich isobars on the right side of this valley. So decay to lower positions in the cradle by electron capture or positron emission. So they try to come to this lower side. So by having some positron emission or by electron capture. So likewise here you can see that these are the neutron-rich isobars on the left side of this valley, and they goes to this side. So by undergoing the negatron or beta minus emission, so they try to go to the more stable state, and these are this valley which is those all nuclides which are having more stability as compared to these upper levels. So the heavy nuclide, they tend to decay by alpha particle or by fission, popularly from these high positions. So these are all undergoing beta minus particle or alpha emissions. So the stable and long-lived nuclei, they are located in the valley. So the stable and the long-lived nuclei, they are located within this valley. The radioactive nuclei, or those easily destroyed by fusion or fission, they are occupying higher positions in this cradle, somewhere like here. So these are the unstable nuclei which are present in this cradle of these nuclides. So you can see from this alpha decay, so alpha decay is occurring in those particles whose atomic number is greater than 83, and they are present somewhere in this nuclear stability belt, and you can see that all those unstable nuclei, they are trying to emit some alpha particle and coming to this more stable form and more closer to this stability belt. So all those particles which are lying somewhere in this region, so they are undergoing alpha decay. And similarly in this beta decay, so this nuclides, they are the beta rich nuclide, and they undergo this beta minus decay and try to attain the more stable position. So all those nuclei which is undergoing beta minus decay, so they are present in somewhere in this green region. And so in this beta decay region, a neutron, it is being converted into proton, and they are shifting down to the right on this stability belt in order to attain more stability. So, and similarly this positron decay, so they are present to the downside of this stability belt. So all those nuclides which are present in this pink region, so they are undergoing beta plus emission or electron capture process and undergoing to attain this more stability by moving close to this stability belt. So electron capture, it is also common in this heavier element. They have a low neutron to proton ratio. So all those elements whose neutron to proton ratio is less, and whose neutron to proton ratio is less, which is lying somewhere here in this region. And beta minus emission is undergoing for those whose atomic to whose neutron to proton ratio is having high. And similarly in gamma radiation, so they are undergoing the radioactive decay process because it carries excess of their energy, and by emitting this excess of their energy, they converted into these radioactive particles. So these are the penetration ability of these various emitted particle from this radioactive substances. You can see that the alpha particles, so they are having very less penetration power, and they barely penetrate in something like a piece of paper. So something cover a distance of in mm or less than centimeters. So beta particle, they can penetrate a few mm to centimeters, so they can penetrate so in few centimeters, while the gamma particles or the neutrons, which is having a high penetration power, and they can penetrate several centimeters of lead. So from this diagram, you can see that the alpha particle, it can be barely stopped with our hand, while the beta particle, they can penetrate from this mass tissues, and they can be stopped with this aluminum metal. Gamma radiation, they can penetrate up to a more larger distance, and they can be stopped by this lead. And these neutrons, which is having a high penetration power, and they can also pass through this lead particle, and they can be stopped by this concrete. So this defines the penetration ability. So that's why, based on this penetration ability, so the gamma radiations and the neutron, they are the more dangerous particles, because they can penetrate within deep inside the tissue, and also cause us bone cancer or skin cancer or some sort of cancers to our body. So they are very, very dangerous particles. So then we will talk about this decay constant. So the number of particles that decay in a given time is proportional to total number of particles which are present in this radioactive sample, and you can use this famous equation. So that is n, which is equal to n naught exponential of minus lambda over t, where lambda, that is known as the decay constant, and it determines the rate at which the material it is undergoing decay, where this n, it is the number of undecayed radioactive material, and n naught, that is the number of undecayed material at time, that is at the start of this reaction. So this is our exponential decay curve, and from this exponential decay curve, we can find out the half-life of a particular material. And you can see that at this start of this reaction, so this is the newly formed material. As the time processes, it is being converted into some daughter nuclei, and it is being decayed, and at this time it has almost decayed. And based on that, we can find out the half-life of this particular decay material using this attenuation equation, and the half-life of a particular material, that is dependent upon this decay constant, and this decay constant, it is different for different materials. So this is the radioactive decay law. So you can see that this is the mother or the parent nuclei which is being decayed and in this form, and from that you can calculate what is the amount of the daughter nuclei which is being converted from this parent nuclei using this equation. And this red line, it is causing how this mother nuclei, it is being converted into daughter nuclei, and the reverse side, it is being also calculated this other way around. So half-life period, as I have already told you, you can calculate using this equation. In some books, they have used the notation of K as the rate of decay, and in some books, they have used the lambda as the decay constant. So let us do one example related to this. The half-life of a specific element was calculated to be 5200 years, and calculate the decay constant. So the half-life period of a particular material is given, and from that we can calculate the decay constant using this formula K, that is 0.693, that is the log of 2 over T half-life period. So log of 2 is equal to 0.693, and on the basis of that you can find out the decay constant of that particular material. And after that, the decay rate. So decay rate of a sample, it is defined as the number of decays which is happened per second, and the decay rate, it is also known as the activity of this sample. And again, it can be defined as A, or it can be defined in as a symbol R, and this decay or activity, that is equal to lambda times the n. So n is the number of particles which are at start of the reaction. So this decay rate, it decreases with the how the amount it is being changed time to time. You can see that at this point of time the decay rate, it is having a higher value, and at the end of this reaction, this decay rate, its slope, it is being decreasing with the time. So decay rate, similarly, we can calculate from this attenuation constant, and the activity of this strength, just a minute, so it is. So the activity or the strength of a radioactive sample is defined as the number of disintegration occurring in the sample, and activity, so this is formula A lambda into NT, and you can see that we can find out the decay rate or activity from this decay constant as well. And the unit of radioactivity, it is called the Curie, and the SI unit of radioactivity is the becquerel, and 1 becquerel, it is equal to 1 decay per second, and from that we can find out the unit in terms of Curie, and 1 Curie, that is equal to 3.7 into 10 raised to power 10 disintegration per second, and most of the time we use the unit of millicurie or microcurie. So 1 microcurie, it is equal to 10 raised to power minus 6 Curie, and Curie unit, it is C into I. So some of the students, they get confused with this symbol of Curie unit. So it is defined as a CI. So how we can calculate this activity of a particular material? So this is another example. So the half-life of sodium 22, it is given 2.6, and from that we can calculate the decay constant of this using this half-life period formula, and the value of this decay constant, it is coming out to be 8.5 into 10 raised to power minus 9 per second. And once we find out the value of this decay constant, and from that we can calculate how many sodium isotopes they are contained within this source. So the activity of source, it is being given 1 microcurie, and from that we have to find the number of isotopes which are present within this source at that time. So using this formula of decay rate or activity, we can find out the number of isotopes of that particular decayed material, and the value of this N, it is coming out to be order of 4.36 into 10 raised to power 12. Because we will use this formula, the value of this decay constant we have discussed, we have calculated in previous slide, and from that we can calculate how many grams of sodium they are present in this source. So as we all know that a gram of isotopes with mass number A, it contains Na isotopes with Na, that is generally defined as the Avogadro number. So 22 gram of sodium, because sodium, it is having atomic weight of 22. So 22 gram of sodium, it contains 6.023 into 10 raised to power 23 isotopes. And from that we can find out 1 gram of sodium it will contain. So when we divide this Avogadro number with the 22, and from that we can find out the value of this N in terms of gram. So the value of this gram N in terms of grams, so it can be divided when we can divide the value of this number of isotopes with this Avogadro number. So these are some of the others, how we can find out the half-life of a period or the activity of a period for different years at this is the value of N at after 1 year, this is value of N after 2 years, so and so you can find out the value of this activity. So once you find out the value of N. So this is another example of radioactivity decay. So in this case, polonium, it has a half-life of 24,360 years. And what is this decay constant? So using this formula, you can calculate the decay constant and how much 1 kg of polonium it is left after 100 years. And from that, you can calculate using this equation. So where T, that is given 100-year, decay constant we have calculated, N whose value that we can find out, and N naught, that is the initial value of is given, that is equal to 1 kg. So we can find out the value of this number of particles after 100 years, so that comes out to be equal to 0.9972. So this is the special theory of relativity, so that the mass and energy, they both are different manifestation of the same thing. So the equation m, that is equal to mc square. So what it show that very small amount of mass, it may be converted into a very large amount of energy, and because these radioactive particles, when they are decayed into some another particle, and based on that they have calculated how this mass it is being converted into energy, and from that we can find out the value of this q value. So that is also known as Q. So that is either it is a endothermic. So on the basis of that we can tell whether the reaction it is a endothermic reaction, or whether it is a exothermic reaction, or how much energy it is being required if we want to generate some sort of particles using this artificial radioactivity. So this energy, mass energy relation, it played an important role by designing some sort of various nuclear reactions. So this is the Einstein gave a demonstration. He said that 1 kilogram of matter, it corresponding to an energy of this huge amount of energy, it is being uh, converted when 1 kg of matter it is being converted into energy. And on the basis of that, he find out 1 ton of TNT, it is liberating this much of energy. So he comes to the conclusion that 1 kilogram of matter, it is converted completely into energy, would be equivalent to energy released by exploding 22 megatons of energy. So from this you can see that matter, or this proton, it is a very small particle as compared to this naturally existing radioactive particle, and from those matter particles we can generate a very high amount of energy as compared to this radioactive material. And so this gives us basically the idea of this nuclear fusion. So that's why the energy released in nuclear fusion, it is very high as compared to energy released in this nuclear fission reaction. So next is the average life of a radioactive material. So the average or mean life of a radioactive element is the all the atoms in the given sample, and it is defined as the ratio of total lifetime of all the atoms to the total number of atoms. And the average life of the material, it is generally represented with the term T bar, and the average life, it is inversely proportional to decay constant. And from that we can relate the average life with respect to half life, that is equal to 0.693 times T bar. So this I have already discussed. In order to have a nuclear decay reaction, so the balancing, it must be checked out. The mass number, it should be conserved, and similarly the electric charge, it must be conserved in this reaction. So let us say we have given these reactions of lead. So when lead is being converted into bismuth, and what will be this emitted particle? Yes, students, tell me. So in this first reaction, what will be the particle which is being emitted out?
A positron.
Positron. Yes, any other? It is electron. In positron, the atomic number, it is decreased by 1, while in electron the atomic number, it is increased by 1. So it is beta minus particle. And same is the case when this atomic number is being converted from 83 to 84. So again here the beta minus particle which is being emitted out. and in this case 84 it is being converted into 82. So atomic number decreased by 2 and mass number it is decreased by 4. So there is emission of alpha particle. So next is nuclear transformation. So since we know that the particles they are being coming out from this radioactive material, so we can also do some sort of the vice versa reaction, or if we are shooting these particles to some stable nuclei, and from that we can see that we can convert those parent nucleus to some another nuclei, and that is known as the nuclear transformation. So when we are doing these reaction forcefully by striking these bombarding particle to our parent nucleus, so here you can see that when alpha particle it is being shooted out at this nitrogen and it is being converted into oxygen plus proton. So here you can see that the mass number and charge number it should be conserved, and only that your reaction it is considered as valid. And in this helium particle that is being shooted at aluminium, and there is formation of phosphorus, and along with that this neutron it is being coming out. And another is transuranium elements. So the elements with atomic number greater than 92 which have been synthesized. So these are the artificially generated or artificially formed elements. So this is with the neutron bombardment. So when we are bombarding neutron to neptunium, and you will see that so there is some particle which is being formed. So when we are bombarding neutron to uranium and this neptunium is formed, and these are some of the particle like americanium, it is also being formed with the bombardment of neutron with polonium, and some positive ion bombardment. So when we are bombarding this polonium with this helium particle, so another new particle it is being formed. So these are some of the transuranium elements, and we have found many new elements by using this transuranium reactions. So these are some of the examples of bombardment reactions, or with the alpha bombardment you can see that the atomic number it is increased by 2 and mass number it is being increased. So you can check all these stuff. So this is another concept check transformation. So here the question is, if we are bombarding americanium whose mass number is 243 with alpha particle, and which lead to the emission of one neutron, and along with that one nuclide which is formed, and what will be the correct answer, which nuclide will be formed? So what will be the value of this X? So here you can see that the americanium it is having 243 mass number, alpha which is having 4 mass number, so total it becomes 247. So when this 247, so on this side, so the total mass it should be 247. So neutron whose mass is 1, so it should be having 246 charge. So the 246 charge that is with this BK element it is being formed. So correct option is option D. So next is alpha decay. So in this you can find out the velocity of this alpha particle. So using this if we are shooting these alpha particle to some high energy magnetic field, and suppose they are moving with the velocity v, and we can find out the velocity of this alpha particle with this equation, that is b q r over m. So that is something like the equation of a cyclotron. So we will discuss in our coming lectures. So how we can accelerate these particles. So B is the magnetic field applied, Q is the charge, and R is the radius of the track with which that particle is moving, and M is the mass of this particle. And next is the range of alpha particle. So range means that distance through which an alpha particle travels in a specific material before being stopped. and the range of this alpha particle, it is directly proportional to the velocity q. And this relation of range with velocity, it is known as the Geiger law. And this relation, when we know that energy with which it is moving, that is known as the kinetic energy of the relation. And the range of this particle, it can be compared with the kinetic energy. So these two relations, so they can also be used numerically. So once we can be find out the energy of the particle is being given, and it is being asked to find out the range of those particles. So this is the Geiger-Nuttall law. So an important quantitative relation between the range of alpha particle and the decay constant. So this side they have find out the logarithmic value of range, and this side they have taken the logarithmic value of decay constant, and they have found that so they are coming in a straight line, and the range of this logarithmic of lambda value, it is equal to a plus b of logarithmic value of r, where r is constant and a and b, they are considered as constant having different values for different radioactivity series. And the range, it can be compared with respect to energy values, and we can also plot the value of this logarithmic value in terms of energy, and then we can find out the value of this constant. So this is the Geiger-Nuttall law, who gave the relation of the range of alpha particle with respect to their decay constant. So R in terms of lambda. So next is alpha disintegration energy. So in this alpha particle, we can find out the Q value of the decay process, and that is known as the amount of disintegrate energy which is being liberated or which is being required to undergo this reaction. Now if you relate or if you compare this both sides, so this parent nucleus, it is at rest, that is our radioactive nuclei, and the value of this Q alpha, it is considered to be positive because the energy is being released from this radioactive nuclei. So on the left hand side, because this is at rest, it's a momentum equation. On the left hand side will be equal to 0, and when this parent nucleus, it is being emitted with this daughter nuclei, along with that alpha particle is being emitted, and you can see that they are moving in opposite direction. In order to conserve this conservation of momentum, so these particles, they will move in this opposite direction, and that's why we will kept this negative sign, because they are moving opposite to each other. So this is our conservation of energy equation, and putting the value of this Vy in this Q alpha equation, and from that we can find out this disintegration energy in terms of kinetic energy. So T alpha, that is representing the kinetic energy of alpha particle. So this is the kinetic energy of alpha particles. And this is also very important equation to find out the disintegration energy of this alpha particle. So next is the quantum mechanical tunneling. So alpha decay is a quantum tunneling process. In order to be emitted from this nuclei, the alpha particle must penetrate or must overcome this potential barrier. And this is similar to the cluster decay in the atomic nucleus, somewhere like for the carbon nucleus, if the neutron, it is being emitted from these clusters, and it should have to pass or surpass this penetration depth of this well, and you can see that the height of this penetration barrier for atomic nuclei whose mass number, it is having less than 200 value, and it is about 20 to 25 MeV. And the alpha particle emitted in this nuclear decay, they have a typical energy of about 5 mega electron volt. And on the other hand, if the alpha particle which is being bombarded from outside, and this, it is being scattered because of this heavy nuclei, and it cannot penetrate, And so 5 mega electron volt alpha particle bound in this nuclear potential well, it is able to tunnel, or it can be passed through this well, and then it can get freeze, and that is known as the wave particle duality concept. So because that can easily pass through this 5 mega electron of energy, and it can easily penetrate and get free, and that is known as the quantum mechanical tunneling. And on the basis of that, we can find out the value of this frequency, oscillation frequency, and from this oscillation frequency we can find out the decay rate. And this is the famous equation of the transmission probability, where T is known as the transmission probability of alpha particle. And using this equation of T, and we can find out these are two constant A and B that we have defined in this Geiger-Nuttall law, and putting these constant value, we can find out the value of this T, and from this T we can find out the decay constant or rate of decay of that particular material which is being emitting these alpha particle. So this is the numerical related with this alpha tunneling. So the question is, in this uranium to thorium reaction, the energy of the emitted alpha particle is this much, and determine the half-life period of this uranium which is being decayed into alpha particle. And you can find out the radius of this nuclei, uranium nuclei, which is from equation R0 A1 over 3. And once you find out the value of R, and you can find out the tunneling probability using this typical equation, and you find out that out of this 10 raised to power 39 strike, so alpha particle which is coming only for the 6th time, and from that you can find out the velocity equation, that is 2E over m, that is our kinetic energy relation, E is equal to half mv square. And from that you can find out with which these alpha particle it is being coming out, and you can find out the collision frequency of this alpha particle, that is equal to velocity over 2r. R you have found from this, and once you find out this collision frequency, from that you can find out this decay constant lambda value. And once you find out the lambda value, and from that you can find out the half-life period of that particular uranium atom. So you will see that how we can find out from a particular given reaction, and if we only know that it is emitting this much of energy particle, and on the basis of this quantum mechanical tunneling we can be able to find the half-life of a particular material. So let us do some of the numerical problems. So in this first question, a nucleus which is having mass number 240 decay by emission to the ground state, daughter nuclei, and the Q value of this process is 5.26 mega electron volt, and the energy of this particle will be. So you will see that the mass number is given, that is 240, and the Q value that is given, which is 5.26 mega electron volt, and the energy of this alpha particle, that is the kinetic energy of the alpha particle which is coming out. And we know that in the disintegration alpha reaction, the kinetic energy of alpha particle, it is equal to Q1 minus 4 over mass number. So in some books it is written as A, so we can write it as A. So Q is 5.26, 1 minus 4 over 240, and when you calculate it, 5.26 into 59 over 60, so that comes out to be 5.1723 mega electron volt. So this is how you can find out the kinetic energy of the nuclei, and the correct answer is option B for alpha particle. So next question is, fission fragments are generally radioactive. So yes, students, what will be the correct option for this? And this is the question of GATE 2007. Yes, any idea? Anyone? Are you listening me?
Yes, sir.
So what will be the answer for this question?
Option A.
I think option D. I con-
Sorry?
Option A. They have excess in neutrons.
Yes, we know that from that stability belt, we can see that for the radioactivity phenomena, the ratio of this neutron to proton, it should be greater than 1.5. And the fission fragments, they are generally radioactive because their neutron to proton ratio, it is almost 1.5 times the number of neutrons have as compared to protons. So having excess number of neutrons, so due to that they are radioactive. So option A is the correct option. So next question is, half-life of a radioisotope is given if there are 10 raised to power 3 radioactive nuclei in the sample, then the number of such nuclei in the sample 4 into 10 raised to power 8 year ago will be. So T half is given, that is 4 into 10 raised to power 8 years. Number of half-life time, so N over N naught you can calculate. So because this is the starting time, so number of half-life time, so you can see that that is 4 into 10 is to power 9 over 4 into 10 is to power 8 is the half-life. So there will be 10 half-life times which will be present in this time. So remaining number of particles after 10 half-life time, so N will be equal to N naught over 2 raised to power 10, and you can find out that N naught, it is N into 2 raised to power 10, which is of the order of 1024 into 10 raised to power 3. So option D is the correct option for this. So you can calculate, I think it's 1204. 1204. Okay. So this is how you can find out if the sample is any time it is given. So next question is, a radioactive substance, it disintegrates for a time equal to its average life. Calculate the fraction of original substance disintegrated. And second part is, half-life is given. What fraction of a freshly prepared sample will disintegrate in 10 days? So you can see that in the first part, the disintegration for a time equal to its average life. So average life, so that is equal to 1 over lambda we know, and from this decay equation, N over N naught, that is equal to E minus lambda T, and T we know that is equal to 1 over lambda, so this comes out to be E minus 1, so that is equal to 0.368. So therefore the fraction of original substance disintegrated, how much it is being disintegrated, so fraction disintegrated, so that is equal to 1 minus 0.368, because this is the value of N over N naught, and this represent how much value is being left. So this is the value which is present at that particular time. So what does it mean? The fraction disintegrated, that is total value is 1, and this comes out to be 0.632. So this is the answer for part A. And second is half-life is given, so that is, just a minute. So half-life is given, so that is 3.82 days, and time is given how much it will disintegrate in 10 days. And so using the same equation, n over n naught, that comes out to be e raised to power minus of lambda t, and e raised to power, so you can find out the value of this lambda from this half-life period. So lambda comes out to be 0.693 over 3.82, and that is equal to 0.181 day inverse. And putting the value of this lambda here, so that is minus 0.181, t is given 10, so this comes out to be e raised to power minus 1.81, that is equal to 3 by 20. So n over n naught, it means this much of the substance it is being present. So what fraction of freshly prepared sample will disintegrate? So how much will disintegrate? So I will write it here, disintegrate, that will be equal to 1 minus 3 by 20, so that is equal to 17 over 20 fraction of the sample it has been disintegrate in these 10 days. So this is how you can calculate. So this is the last problem of today's lecture. The half-life of UX1, it is 24.1 days. After how many days after UX1 has been isolated will it take for 90% of it to change to UX2? So UX1, it is being disintegrated into UX2, and we have to find after how many days it will be disintegrated 90%. So n over n naught, that is exponential of minus lambda t. So half-life is given, we can find out the value of this n naught. So here 90% of is being disintegrate. So what does it means? How much it remains? It remains 1 minus 90 over 100, that is n over n naught is 10 over 100 remains, or you can see that the ratio of n over n naught is 1 over 10, it remains. So lambda you can also calculate. So lambda comes out to be 0.693 of 24.1 days, and putting the value in this equation, so this comes out to be 1 over 110 e raised to power minus 0.0287 into t. So this t we have to find within how much time it will be disintegrate 90%. So you can find this t, that comes out to be log of 10 over 0.0287, that is equal to 2.3026 over 0.0287. So you can use this logarithmic calculators in these examinations. So t comes out to be 80 days. So this is how you can find out. So here the important trick is most of the students stuck in this portion. So this n over n naught is that ratio which remains at that time. So the portion which is being disintegrated, you have to subtract it from 1 in order to find the exact number at that time. So this is the end of today's lecture, and in our next lecture we will discuss the Fermi theory of beta decay, and then we will discuss the various selection rules and what are the allowed and forbidden transitions, the spectrum of beta decay, and all those important numericals related with this beta particles emission. So if you have any doubt, you can ask